Recording in progress.
Here we go. Okay, so 7.5, those are the answers. Very important. You know it's opposite, know it's adjacent, know it's hypotenuse. Hypotenuse is straightforward, it's just a slanted side. But sometimes if the triangle is oriented in a funny way, which it can be, the hypotenuse is strictly the side opposite 90 degrees. That's it. That's all it ever is. It's also along the side too. The adjacent is going to be next to the angle he's talking about. True, the hypotenuse is adjacent technically, but we call the adjacent a leg. A leg is one of the sides that makes the right angle, right? It's one of the sides of the right angle, and it's a side that's right next to the angle that we're interested in looking at. The opposite clearly is the side opposite the angle that we're looking at. There's only one side opposite, right? And there you go. So for 7.5a, clearly we want x. Clearly we're given 28. X is the opposite of 44 degrees. 20 is adjacent of 44 degrees. So think like that. How is the side related to the angle? O over a, that's TOA. So you got to go tangent. Once you set it up, then your goal is to isolate x, which now that comes down to algebra, and that's all. Now b is a little funny. That's a cosine because you have adjacent or hypotenuse, but the variable is on the bottom. Most students who struggle with this, like this one's pretty easy. I think most people know, yeah, multiply 28. Give it the set aside, right? Likewise with C, we find out once that's sine opposite of hypotenuse. But where students struggle is when the denominator has a variable. And the reason why you guys, well, not you guys, but students in general struggle is because of fractions, right? They just get freaked out, like, oh my God, there's a variable in the bottom. What do I do? Don't freak out. It's just an extra step. Multiply by x, just like you multiply both sides by 28 for part A, and then you get the answer. Same thing here, multiply by x, not a big deal. But it's one extra step. After you multiply both sides by x, what's the next step after this? Divide by what? Well, how do you get x by itself? You got to divide by what? Cosine, right? That's why I'm so bent on like all those like the literal equations and moving things around, because I need to make sure the algebra is clean with you guys, right? Because we can't have algebra. Algebra cannot be an issue anymore. Can't. We're well past that. Now we're doing trig. You guys move on to pre-calculus next year, where it's all even more trig, any more advanced stuff. So we can't have this be an issue. If it is, talk about, work with you on it. But yeah, that's what you get. And you get 176.88, as you should, because it should be the longest side. If you got something less than 150, you made a mistake, right? Because it can't be less than 150. All right, I'll get off my soapbox. Let's, oh boy. All right, this is a little crazy. It's not very clear. The 46 is actually only part of the bottom side. So I kind of labeled A as one side, C as the side, B is a height, and D is the other portion that's next to 46. And so I did sine 70 degrees to get A, and then I did cosine 70 degrees to get B. And then I did sine 44 to get C, once I knew what B was. And then I had to do cosine 44 to get D and add it to 46. And then for the other one, kind of same thing, label four sides. A and B are part of the same side, but A plus B is the big side, right? The bottom side. C is the height, D is the hypotenuse of the right triangle, the right triangle off to the right. A is easy, that's 16.5 because it's 30, 60, 90, right? And C is 16.5 root 3. I can do sine 42 degrees when I focus on the right triangle off to the right. That will be 16.5 root 3 over D, solve for D, and then do cosine 42 to solve for root B. Once I get B, add 16.5, we're good, we got it all. 7.15, here we go. Label sides. We know 30, 60, 90, 1 root 3 and 2, 1, 1 root 2 for 45, 45, 90. And why is 30, 60, 90 half of an equilateral triangle? Well, equilateral triangle, what does that mean? It's equilateral. All sides are the same, all angles are the same. Split that in half, you get 30, 30, and that's 60, 60, hence 30, 60, 90. So you can actually derive the ratios from that, right? Because if you're splitting an equilateral triangle, x and 2x. So I did say there was some memorization, but not really actually. Taking 30, 60, 90 and labeling sides like 2x, 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 or even x, 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 and that's x with 2. You'll find that that's root 3 times that side. We do that here. And that's where the ratio comes from. And then for 7.16, yeah, just do sine, easy. And make sure you do the inverse sine function in the calculator, which is second sine. Make sure you're in degree mode, because you will get a wrong answer. You have something called radians, which doesn't make sense. And I lied, we're not doing radians today. I think next week we'll do radians. Today we're going to talk about the sine equation. how that actually looks, how that graph looks. And the serial boxes, you'll see how it plays a role. 7-8 is a brutal problem. I never gave you guys a problem like this. This definitely would be like kind of like the extra practice, or if you're trying to gear up for pre-cal AB honors, this is the kind of problem you want to do. Actually, for those who are looking to do pre-cal AB honors on the placement test, which I think is sometime next month, you might see a problem like that, because it forces you to think a little bit outside the box. Like, hey, wait one second, I got 2 radicals, but I have a +5. What do I do with that? Square both sides, and the left side's fine. It's cleaned up. The right side's not clean, unfortunately. You got to FOIL with itself. 5 plus √3x minus 6, FOIL it. You get 10 √3x minus 6 in the middle, 3x minus 6 off to the right, 25 off to the left. Move all terms to one side, so isolate the radical as much as you can, then square both sides again. It gets incredibly nasty. And then you get this. And I had no clue how to factor that. Even someone like me, I can't factor that, so I did quad form. Fortunately, it came out clean, not a nasty radical. The inside part actually was a perfect square. 720 apparently. And then you just do 1210 plus that, 1210 minus that, you get 2 answers. So 7, 9, I did over here off to the right. Easy. Complete the square. In case you guys forgot, you got to take half of 5 and square it, add to both sides, or you could add to one side and subtract on the other side. Sorry, add and subtract on the same side so they cancel out. But your goal is to back this, which is x plus 5 times squared plus 3/4. And then you identify the vertex, and then the y-intercept is easy, just play with 0 for x. And then graph it all. In terms of symmetry, if I know the y-intercept and I know the vertex, I can go 5 halves in the other direction, get the same y value. Um, (710), find x and y intercepts. Yeah, it's easy. Plug in 0 for x, solve for y. That's easy. I get 88. But when you plug in 0 for y and solve for x, that requires a log. Unfortunately, you can't do that. So it means that this does not cross the x-axis at all. In fact, it wouldn't, because if you add 7 to both sides, that shifts 7 up. So the graph looks like this. It never touches the x-axis. Forget about it. Just doesn't happen. So forget about it. It doesn't work. So, okay, questions? Cool. All right. So now let's move on to the notes for today. So you have the notes in front of you. Here we go. Yeah, go, yeah. Go ahead. Don't know why my computer's slowing down. Oh my goodness, what is going on here? Okay. That's the homework. There's a classwork. Okay. All right, I'm gonna actually, for the table in front with Jack, Sophia, Hunter, and Charlotte, I'm gonna kind of help. I'm gonna use their box to help you guys make sense of this. So this is kind of a little story that goes with this. We'll kind of just read it out loud, just to kind of understand the story. And then I'm gonna tell you mathematically what you guys are gonna do. And then we're gonna plot some points. And you guys are gonna actually discover the equation for a sine graph. Or sorry, you're going to discover how the graph of a sine equation looks. That's what we're going to work on today. Okay. So let's go and read through this little storyline here. We'll take turns because my voice should take a break. So I'll kind of just go around the table, the room, and have one person at each table kind of read a paragraph. So we'll start this table here. Emily, you want to read the first paragraph where it says hurry?
Let's get there before the line gets too long. Shouts Henry to his best friend Oliver as they race to get on the street. An early attraction at the local amusement.
Thank you. And then Pierce, can you read the next paragraph? It's only been. Okay, so just more about the story. And then table in the back. Evie, can you read Henry Whistles? Okay, before we read the next paragraph, just explain what's happening. Good, actually, guys are skewering. What you're gonna do is you're gonna be taking the zero blocks. And you have two circles. You have a white circle and one with a, I don't know what they call it, like clear paper or I don't know, just plastic. Yeah, some plastic. There you go, plastic. There. And you're gonna kind of rest it like this. You have these notches here too. You need to make sure the notches kind of rest on zero blocks. And you know what makes things have Y kind of exposed, right? And then you're gonna take the skewer. You just skewer it to the middle. There's actually a hole there. And you're gonna start rotating. And then yeah. I'm gonna tuck that in like that. There we go. I don't want to show you this, guys. Now you want to keep the oh. See, I'm like just a little doofus right here. We go. Okay. That's where I do this, guys. All right. Okay. I think you probably need 2 people reproduce, but yeah. Yeah, I'm just a little more right now. I knew this was gonna happen to me. Okay. Okay. I think I got now. So yeah, oh here we go. You want to hold the light part and rotate this around. There we go. I got it now. All right, I'm good. I'm good. I think so. Anyway, let me screw this a bit more. There we go. Okay. Yeah, so you're gonna keep the white part stable and the plastic's gonna move around. You probably people must have that's get down. Yeah. Ah, so much better. Okay. Yeah, you can see why this has to be good. Okay, now I got it. So what you want to do is you're gonna set up such a way where you're gonna rotate this. And every tick mark, someone's gonna sit on the tick mark. So like for example, you see here, let's say there's 5 tick marks in each quadrant. And of course you have the top, the Y, and some other ones. So I think there's actually a total of 24 to 25 seats. So like each person's gonna sit here and you're gonna rotate it. Now when you're above, you're nice high from the sky, right? When you're below, that's the murky pits. So that's what the story is all about. So you're gonna be sitting on this like ride, and parts of you below, parts of you above. What we're really gonna do, the whole objective of this, is you're gonna measure the height you are off the ground or below the ground. And that in itself will lead to trig understanding. So that's kind of the whole point. And you have these little rules here to measure wherever you're sitting on the Ferris wheel, this ride, how far you're off from the ground. And also it depends what angle you're at too. So that's kind of part of this activity. I've never taught trig this way, so we'll see how it goes. I'm actually thinking this might be better than the way I've taught in the past. But what you're going to do is you're going to be taking a circle and rotating it above and below the little slit where the zero box is. So, yeah, go ahead. All right, let's read the next paragraph. So if you want to read where it says Oliver and Henry.
Rotates 15 degrees to rotate the next to the branch. When Oliver straps himself into the motor carrier on its really had to rush to get it done.
Okay, thanks, Sophia. So I'll read the last part. So again, every tick mark is 15 degrees. If you think about how many degrees is a full circle, guys? Well, how about half? How about a quarter? And then if you break that down by 6, 15, 30, 45, 60, 75, 90, right? So that's how this is broken down. It's broken down to 6 within each quadrant. Sure enough, just as the ride plunges Oliver and Henry into the grease of water, they hear the piercing scream of metal twisting. Sparks fly and the pit fills with smoke as the ride grinds to a halt. To escape, all the passengers must. So basically, the ride actually breaks down. Okay. So they load the passengers, and then all of a sudden you're stuck. So to escape, all the passengers must climb vertically to ground level from where they got stuck, or they got to climb up from the pit or down from dizzying heights. So basically, you have to climb. You have to climb to get back to the ground level, or climb up. So your task arrive function describes how far above or below the platform a rider is when the screamer breaks down. Okay. So here's the deal. Okay, and I kind of obviously somewhat messed up when I tried setting this up. So to help get you gather data, so this is the teamwork part. Your teacher will provide you with materials to build. Okay, this has already been built for you. So Ms. Wong actually did all. She got the cereal box, she cut the slit, she made the circle. So thank you to her, and she brought pie. So first, mark all the seats in the cardboard circle, which you guys this is done. Each is 15 degrees apart. So you don't need to do that. That's all done for you. Insert a wooden skewer, so you'll need to do that. Then slide the cardboard into the slit, into your cardboard box, as shown in the diagram to the right, and use a cable zip tie to show where your seat. Don't worry about that. Okay, use the cardboard 1-unit ruler, which you do have, to measure escape heights on the model for at least 16 different possible seat positions. So I'm going to help this table here in front to get things started, just so you guys know how this works, and then you guys will fill out the rest. Remember, this position depends on the angle of the ride's rotation or broke down. The radius of the model wheel will be referred to as 1 unit. Remember, the model of 1 unit corresponds to actually 100 feet on the ride. So remember, the radius of the ride is 100 feet. So the highest you could be is 100 feet off the ground. So the highest you have to climb down is 100 feet, or climb up from 100 feet from below the ground. So an actual height of 80 feet will correspond to 0.8 units on the model. Record your data in a table like the one shown below. Okay, so here's what we'll do. I'll get us kind of kickstart here. So let's look at 15 degrees. Let's look at 30 degrees, 45 degrees, 60 degrees, 75 degrees, 90 degrees. And then in the interest of time, we're not going to do them all. So I'm going to kind of skip some numbers. So these are all the ones we're going to investigate. Give me a sec here. Okay. So these are all the ones we're going to investigate. We're going to investigate all those angles. We could have done more, but we'll do 16. Okay. So I'm going to help this team out. So yeah, make sure I can do this right. Yeah, it's going to be some scratch. Okay. So yeah, what you should do first is take the paper and the plastic, and I'd say I would line up in such a way, see wherever you want. Line up to see at 15 degrees. So what you want to do is take your plastic, take the white circle, right? You see a notch that says seats on the white circle. Have that notch where it says seats line up at 15 degrees for the first tick mark, right above X. We kind of line up like, see how I have it kind of lined up like this, right? So see the plastic notch is a bit below the white notch, and skewer it. Yeah. So then you're gonna rest it. You know, I think you're right. You know what? Yeah, actually, Jack's smarter than me. Only time would be the second. No. Anyway, so what you do is, move the white. Yeah, you move the white. That's right. So you move the white notch. So first of all, have it lined up like this. So have it lined up like this, where you see it Y up top, X to the right. Both plastic notches resting on the cereal box, and you're gonna move the white circle. So each one's 15 degrees. They're not 50. So what I'm gonna do is I'm gonna move the seats about 15 degrees. Okay, hopefully you guys can see that. Those kind of to everybody. Right? Holy mystery, right? Okay. Yeah, good. Look, you got that. Yes, I'm good.
From going to 10 to 11, shouldn't it be?
I skipped it.
Okay.
Yeah, I a little bit skipped it. Okay. All right. So now what I'm going to do, I'm going to take a little ruler that Jack's one. I'm going to measure how far the seat is. So when I look at the seat, I'm looking at where the line hits the word seats, that little like thin black line. And I'm gonna measure it from the box, which looks like it's about 0.3. If I'm not mistaken. And actually, let me make sure. Yeah. One step here. So make sure this accurately.
How do we form like the directions?
Okay, actually what you want to do, guys, just be careful. Measure the distance from the seat versus seat, and that line that touches seat, to the x-axis. Don't do it to the box, it's gonna be off a little bit. So just kind of show you guys right now, like from 15 degrees. Yeah, so basically from basically where it says, see that line where it's seat and the x-axis looks like it's about 0.25. Yeah, get about 0.25. Yeah, so what you want to do. Actually, person contacting it.
One unit of 400 feet.
So yes, you go through it. Eyes or seats like so that's so.
So, yeah, so let me just show one person that they kind of know. I don't know what you said.
Paper. And I'm not like, I'm not just gonna copy it. I just knew like the road. The radius is anywhere from the x-axis. Yeah, the radius of the circle, this circle. Yeah. I mean, where does it say that?
Okay, let me make sure. That's how we're measuring.
Is there another box radius?
Don't worry about it, you mentioned the x-axis anyway.
So you know this is gonna be a high.
So yeah, to see how like. See how it lines up with the series. So what you want to do is here's to see that line.
Diameter.
You want to measure that height from the x-axis to that. Which looks like it's about 0.25. And you're gonna keep rotating it. Okay, so you guys can take turns, like somebody can record, somebody can measure. Someone can convert. So I'm gonna do the first couple of you guys. So this right here was about 0.25. So that corresponds to 25 feet. So these are in inches, by the way. And that's in feet. So you simply multiply by 100. That's what you do. So the actual is 100. 100 times the measured height. Okie dokie. So 30 degrees.
How do we find that it was? How do we find that?
Oh, because we're assuming this is 100 feet in actual, so it's just a ratio. That's all. Because right now the measurement right now is 1 inch. Well, actually, it's not 1 inch. I don't know what it is, but the bottom line is the scale here is 1 inch. 1 inch corresponds to 100 feet. So basically, you're doing. It's not really inches. I don't know why I call it inches, but so the bottom line is you're multiplying the measurement by 100.
So what would 30 degrees?
Let's do it right now. What do we got to measure first?
How do you measure it?
So you rotate 30 degrees, right? And then what you do is you take your ruler, measure from the seat to the x-axis, which I think is 0.5. Yep, 0.5. All right. Yeah, so the next one's gonna be 0.5. And I don't know why I wrote inches, guys. It's not really inches, but anyway, it's fine. That's 0.5. So that's 50. So you kind of just keep going. And you might have to estimate a little. Oh, sorry, I took yours. Yeah, so you're just gonna just do the rest of these. You'll start noticing some patterns. Okay. I'll kind of pause for a moment, let you guys kind of work it out. I kind of know what's gonna happen because I have done this before, but yeah. So take some moments to fill this out. I'm gonna fill it out myself. I'm gonna freeze my screen for a while. I kind of know what to expect.
Should we measure it so the very outside of the west?
Yes, 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 100%. That's good. That's good. You got 0.7 for 45. Good.
Make sure the measure is the top left. I'm measuring. I'm trying to show you. Let's do it. I'm measuring it from the top of this. Yeah, that's what you were getting. The 90 double check. The 90 should be one or 9. It says go, 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 go. It says you should.
And at least try to get up to 150 or 180. I'll kind of help you with the last few.
1.0. So 90 has to be in this one. I don't know where the rest of them are. What you get for 90 degrees?
1. Because you're at the top.
Do we measure it from the box or the purple line?
From the x-axis.
Okay, that's what we did.
Yeah, yeah.
But we're not getting where.
It's a,
We need a ruler.
oh, yeah, there's not one that message taking yours.
Mystery, for the ones underground, do we do it in negative?
Yeah, exactly. So actually, when you get to underground, you can't really measure it so much because it's underground. So let me show you what's happening now. Here we go. Okay. So the first quadrant, I stand kind of these. If you're close enough, it's fine. If you said 0.9, whatever. But you multiply it by 100 to scale it up. So like 90 degrees is 1. And then what you notice that when you see 120, 135, 180, you're gonna start noticing some of these are repeated from the first quadrant, right? And then you can't really do the negative ones once it gets past 180 because now you're below. Like you're in the scary murky pit, right?
You just like go backwards.
Yeah, yeah, too. Sure. Yeah. But those would be negative values, so now they have to climb up. And so you'd have that. So what I did was I kind of used symmetry in some ways. Like for example, 210 is 30 from 180. 150 is also 30 from 180. So I figured 210 and 150 are very similar. 225, 235 are very similar as well. Let me actually get a highlighter so you guys can see the similarities among these. Color coding, I think, will help you guys. So this and this are kind of the same thing, right? That is really hard to see. That was terrible. This and this are kind of like the same thing, right? or like this and this are kind of the same thing. Or if I get another color, yeah, those are some that blend in a bit too much. If you're colorblind, I always, but they're like lavender and like bluish, purple and bluish, I don't know. But 90 and 270 are very similar. 122 are very similar. 135 2.5 very similar. 152 very similar. That's just all about symmetry. That's be a big part of understanding how a sign graph looks. It's all about symmetry. And what I'll do is let me copy.
0 is 180.
I'll paste that in just a sec.
0 is 180.
I'll let you guys copy if you're still copying. Okay, let me take a screenshot of this. Okay, so in case you need to see it again, I'm gonna move my screen. Okay, now what we need to do is we need to graph this. Yikes. Okay. So what I'm going to do is I'm going to plot these. So 15 degrees. Let's plot this in blue. So yes, exactly. Yes, yes. X is a degree. So this is X, and that's me Y. Okay. So at 15, I should get 0.25. By the way, you get 0 over here because you're not off the ground. At 30 degrees, I should get 0.5. At 45 degrees, I should get 0.7. At 9 degrees, at 6 degrees, I should get 0.85. So it kind of slows down a little bit. At 75 degrees, I should get 0.95 and 1. So the curve kind of looks like this so far. Then at 120, I should get 0.75. Is that right? No, 0.85.
Would you get for 75?
0.95. At 135, I should get 0.7. At 150, I should get 0.5. At 1, I should get back down to 0. Okay. And if I keep plotting, and let me erase a portion of this. I don't need all this now. Yeah, if I keep going, 210 is at negative 0.5. 225 is at negative 0.7. 240 is at negative 0.85. 270 is down here. 315 is at negative 0.7. And so what I just did, without you guys realizing it, this is the graph. I'm going to explain why it's the graph of sin x. Where x right here is in degrees. And y here is sine x, or the height off the ground. The height off the ground. I'm not sure if you guys can read that. That is terrible. Let me do better. Let's see here. Red. That's a height. Ben, go ahead.
This is like a graph of like, what's this supposed to be?
So for now, all we know is just we're comparing the height off the ground with the degrees, right? Because that's what we did. We measured how high the person was off the ground, depending on where they were on the ride. But what we're going to notice eventually is that as we were doing this, like, if we had like, this, we had this wheel, right? And so you had this here, and this is 100 feet, right? Actually, technically, that was 1, because that's a radius. And here's the angle. What do we actually measure? That's the height, right? If you think about it, if that's theta right there, sine theta, isn't that the height divided by 1, right? So that's what we're really measuring. We're actually measuring the sine of these angles. And when we're actually using that ruler, you're actually measuring the sine of whatever angle you're at for that seat that you're sitting on. That's actually what we're doing here. But for now, this is high off the ground versus degrees. For now, that's how we see it. Now, suppose you add 20 more data points to your table. What shortcuts could you use to reduce the amount of work? Symmetry. Totally symmetry. 100%. What does that mean? So for example, when I had 0, I had 0. When I had 30 degrees, I had half, or 0.5, right? When I had 45 degrees, I had 0.7. When I had 60 degrees, you don't have to write stuff down. It's already written, but that's 0.85. And when I had 90 degrees, I had 1. So if you think about symmetry, right? What if I look at 120? How far is 120 from 90?
How far off is 120 from 90? 30, right? How far is 60 off? 30. So they're going to share the same black coordinates.
That's also be 0.85. So if I added, like, say, a weird angle like 80 degrees, that's not weird, but then I would do 100 degrees, right? And I would get the same thing because you're looking at symmetry. So if you add more data points, what shortcuts you use to reduce the amount of work? Just symmetry. So now let's take a look at 713. Let me readjust. The function that models the situation 712 is a new parent function. To help you figure out what it is, sketch by try. I already told you it is. So like, for example, this is 1. That's our radius, right? That's our height. So how do I write an equation to represent this? Sine of 40 degrees equals what? The height over 1. So the height, where sine 40 degrees is, 0.64. Or 0.643 would be a little more accurate.
Why is it over 1? Couldn't it just be?
Because the hypotenuse is 1.
Because in our circle we did, right? If I, what was the rule? Yeah. If I actually measured from here to the seats, it's going to be 1. And we have to put a little. No, I'm just trying to show you what we're divided by. Because sometimes the rates could change. Oh.
Sometimes it could be a different rate, it could be a little longer radius, right? But it won't matter in the grand scheme of things.
Oh, since
it's all proportional. Exactly right. Exactly right. Right. So the height of any passenger on the Screamer ride can be thought of as this: h of theta just equals sine theta, or opposite over hypotenuse, where that, remember, was the radius and that was the height. Remember, our radius was always 1, but the height varied. So you can get the height of yourself off the ground as a function of theta or sine theta. And lastly, we're going to punch this in the calculator so you can kind of see this in action, how it's very similar to what we just did with this little project or experiment. And after that, then I think we're done. Okay. So here's what I'm gonna do. I'm gonna pull up my calculator. You guys can just watch. Why is my computer? I gotta restart my computer. I don't know what's going on. Yeah, I'm just gonna close a bunch of windows down. Okay. Here we go. Oh goodness. After closing everything down, really? Here we go. Oh, Hunter, I love that jersey. That is hilarious. Yeah, from Superbad. Which actually is really funny. It has 2 Academy Award winning actors in that movie.
It does.
Well, Emma Stone. She won 2. And Jonah Hill. He's been nominated a couple times. It's for such a goofball movie. That's pretty impressive.
It's an old movie, like
It's an old movie, but another one that's kind of like a what do you call it, coming of age film. So back in the 80s, a really popular one was Fast Times at Ridgemont High, which you have like this like one really strict teacher and his total stoner. Sean Penn, Academy Award winner. Forrest Whitaker, Academy Award winner. Nicolas Cage plays a small role, Academy Award winner. Like it's funny how these funny movies. Anyway, I digress, guys. But he got nominated for Moneyball, and I think maybe Wolf of Wall Street. I don't know. Jonah Hill, I don't know, but he was great in that movie too. And then like Tom Hanks, like he did like these silly movies called Bachelor Party and
oh yeah,
Crossdresser in a TV show in the 80s, like, and he's like an acclaimed actor. Like it's just so funny. Like these actors
I feel like they all go from
they go from like total goofball to like serious acting. So when I see him like McLeod, I just remember
Jordan Peele did that.
yeah, right. And like he wrote a great script. Well, Get Out. That's an incredible script. His first time. It's you know talks about race a lot and yeah, it's pretty. Anyway, if I could teach a movie class, I would. I love movies. So anyway, just talk about the themes. You know. All right, here's what we're gonna do, guys. So I digress. My apologies. It's just Hunter had a really cool jersey that was really funny. All right, so here's what we're gonna do. For part C, and this is just being, of course, you guys can watch this later. So if I want to graph sine, just go to mode, switch to degrees. We'll talk about radians another time. Y equals sine x. Now, if I want to make a table for it, I'm gonna hit second graph. Actually, I take it back. I get second window. I'm gonna start at 0, but I'm gonna set this at 15 degrees. So it only goes every 15 degrees. And then hit second table. And you can see how it gives me all these y values we just got. Right? 0, 0, 15, 25, 30.5, 45.7, 16.86, 75.96, 91. So it actually shows you, and if I were to just simply scroll down, you can see the symmetry that's happening, right? And then it becomes negative afterwards. And then it goes down to -1, it repeats itself, right? And then all of a sudden, when you get to 360, then a full circle, it repeats itself again. So by the way, you can do the sine of like angles more than 360. You can do 375. You do 390. It's just gonna be equivalent to like for the first rotation. Or you can go backwards. Hold on, Ben. Or you go backwards and make it negative. That's another thing. Like, does the right have to go counterclockwise? No. It didn't have to go counterclockwise. It could have gone. And now my computer's super frozen. I don't know what's going on here. Hit second window. And then make sure it starts at 0 and make the delta, the triangle, 15. And leave everything else on auto. I'll go back.
Okay, okay, no.
And then hit second graph afterwards. But see, you have all the negative angles here too.
So it should be
That's a possibility. Yeah, second window. Like right now I'm at negative 90. I'll do 0 and hit second table. And there you go.
Which where did I don't have any y.
Oh, because you didn't punch it in first. That's why. You gotta go y equals sine x.
Oh,
There we go.
just in that thing.
Right. So what happens when you do this? How does this compare? It's the same. Same thing. That's how it compares. So what does the graph look like? Well, if I hit graph, let's go back to the calculator one more time, then I'm done. Hit second window, and then make sure 0 is starting and 15 is the change, and then hit second graph to see the table. But you have to type in the equation first. Do you have the equation typed in? I've made it 15. 15, yeah.
Mr. B?
Yeah.
Put sign X or Y?
Sign y equals sign x.
Or where does the equals?
No, go to y equals first. Top left corner. Right? That's the inter equations. Okay. Now when I hit graph, I don't see anything, right? When I hit graph, how come I don't see anything? What's the window here for this graph? What's the x window from -10 to 10, right? Yeah, and look at the y, it's -10 to 10. So what I probably should do is go to window, change it from 0 to 360, so I can see a full circle, and make that 15. And then tighten this, made from like -2, 1, sorry, 2, and 1. So now I can see the graph better, right? So you also have to be mindful of the window. So going back to window, if you want to see the graph, we knew we're graph from 0 to 360 because the graph repeats itself after 360 degrees. Because now you've gone around the whole ride, right? Because how does the ride work? You say board over here, you rotate, and then you go below, and you come back up again. You travel 360. That completes one cycle. And that's what's happening with a sine graph. It's completing one cycle. This will also lead to something new called the unit circle, which we'll talk about next week. That's kind of a big deal. Usually I teach that first, but it's a very dry, boring thing. I think this is a little more tangible, a little more visual. It's a little better. And the graph of sine x, of course, is just this. The graph is just this. Where it's 360 degrees. 1, -1. So yeah, that's what's happening. Okay, notes are done. Homework's right here. Homework, just using the calculator. Well, it says don't use your calculator. So yeah, actually don't use the calculator. But it's just actually using the special right triangles we did in on Tuesday. 30 degrees, right angle, 60 degrees, 1/2 √3/2, or 45, 45, 90. One, and √2. And then here for number 2 is asking to write the sine, cosine, blah, blah, blah. More of the same stuff as before.
Wait, how do the first one?
Oh, just use the ratios of 30, 60, 90 from your notes on Tuesday.
Okay.
Yeah.
Oh,
Yeah, notes on Tuesday. And then the screamer, it's just more figure out the heights of those different things. Just use your table that you got. And it's just old stuff. Just make sure you guys don't forget old stuff. So, and that's that. So we'll go ahead and stop there for today. And this homework is due Monday. Remember, we don't have a test before spring break. We're not going to rush this. This is brand new stuff. We're going to take our time with tricks as we should.